gosh, this test is tomorrow. What was an integral again? Oh my gosh, I don't remember. I got this. I can do this. Oh, kittens. No, Marissa, you just gotta focus. You can do it, just like Shia LaBeouf said. Just do it. Okay. Alright, I'm ready to go. I got this. Let's get an A. Gosh, that was not very good. Oh, I hope I passed.
And here's your test, Marissa.
When you try your best, but you don't succeed.
No! Oh, my arm's tingly.
Oh no. Someone call 911! Oh, hi. I'm glad you're awake. Do you know where you're at right now? Well, unfortunately you did have a heart attack. Right now you're at the university hospital. Can you see and hear okay? Okay, perfect.
But doctor, what kind of test did y'all do to me?
Well, like I mentioned, you did have a heart attack, and we were checking for any heart damage. So what we do is a process called thermodilution. Thermodilution checks for any cardiac output.
So doctor, what's the cardiac output gonna tell you?
I'm glad you asked. Cardiac output is a valuable aid to the diagnosis and treatment of heart damage. It is the volume flow rate of venous blood by the right ventricle into the pulmonary artery and then into the lungs.
Alright doc, that's kind of complicated. I need a visual here.
So in thermodilution, a balloon-tipped catheter is inserted into the arm vein.
Oh, like this?
So once it's inserted into your arm vein, the cold room temperature injectate is introduced into the right atrium through the proximal injection port of the pulmonary artery catheter. So right here. The injectate solution then mixes completely with the blood in the right ventricle, and then the cooled blood then flows into the pulmonary artery, and a thermistor on the catheter registers the change in temperature of the blood, and that all occurs right here. So basically, we just injected water into your body, and we're recording the change in temperature. So what exactly were you doing when you had the heart attack? After looking at your results, I can see that there was certainly some stress involved.
Well, doc, I'd rather not say. It's actually kind of embarrassing because it happened because...
What?
Because I was studying for a calculus test, and I got really stressed out because I got an F, and I don't understand anything that goes on in the class.
Oh. If you want, I can try explaining some of this process that I was just showing you using some calculus terms. Maybe it'll help you pass your class.
Oh my gosh, doc, that would be great!
So the quantity of cold that we're measuring is defined as Qn equals the volume and then the temperature final minus the temperature initial. So V is the volume of the injectate in milliliters. TF is the body temperature, and TI is the temperature of the injectate we're injecting into you. So after measuring your body temperature, it was 37 degrees Celsius. The injectate was 0 degrees Celsius, and we injected 10 milliliters of it, giving us 370 milliliters per times Celsius. So the quantity of cold passing by the thermistor in a short time interval, dt, can be calculated by multiplying the flow volume FdT and the temperature variation delta T during the interval. So therefore Q out equals the integral from 0 to 50 F delta T dt. This graph right here shows the temperature change within a minute after you were injected. As you can see, there is a significant increase in the slope of the graph after 5 seconds, which means that is the interval in which the cold injected is just mixing with the blood, causing the temperature to severely fluctuate. Afterwards, the temperature of the blood stabilizes, in which we see a decrease in the change in temperature being recorded, explaining why the graph's slope stabilizes from the interval of 15 to 50 seconds. The area underneath the graph is one of the parts needed to solve for the cardiac output in your body, and is why the equation that I just showed you was asking for the integral from 0 to 50. This table helps us visualize the numbers from the graph more efficiently of the change in temperature occurring in your body after you were injected. This table also facilitates finding the left and right hand sums of the graph, which afterwards can be averaged out to find the best estimate of the integral from 0 to 50 seconds. After calculating these numbers, we found the left-hand sum to be 4.9, which was an underestimation of the actual integral of the graph. The right-hand sum, being an overestimation, was 4.945. The two numbers were then averaged out, resulting in 4.925, which after calculating the actual integral of the graph, it was nearly the same, showing the accuracy of the average between the left and right-hand sums. So we're assuming that there's a conservation of cold, and therefore, since the cold is being conserved, Q out can be substituted by Q in. Therefore, Q in being V T final minus T initial, we can solve for F by dividing by the integral from 0 to 50 delta T dt. Once we solve for this, algebraically, F is equal to V T final minus T initial divided by the integral from 0 to 50 delta T dt. So this variable right here, F, is what's measuring the flow rate. The flow rate is the cardiac output, as I was explaining earlier. So to calculate what your flow rate is, we already calculated this, which we knew was 370. After calculating this on a computer, it comes out to be 4.92. This gives us 75.187 milliliters per second. Now, the flow rate should be measured in liters per minute. So to convert it, we go from 75.187 milliliters per second. We know that there's 60 seconds in 1 minute and 1,000 milliliters in 1 liter. And after converting it, this gives us a 4.51 liters per minute. This right here is your cardiac output.
Alright, doctor, I see what you're saying. But, you didn't tell me the bottom line, though. Am I okay, or am I ill? Well, obviously I'm ill because I had a heart attack.
So, the normal resting cardiac output for a patient is around from 4 to 5 liters per minute. Someone who is critically ill is normally falling below 3 liters per minute. So using the fact that you're at 4.51 liters per minute, you tell me.
Oh my gosh, are you telling me that I'm actually okay? Oh, this is so great!
Whoa, easy there, easy there, easy there. You need to go back to bed. You're okay, but take it easy.
Oh, okay. Sorry, Doc. I'm just really eager to take my next test. I really think I can make a good grade now. I'm so excited.
So I know you have your test in a couple of weeks. you'll be ready by then. Just make sure you rest, drink some water, and you'll be out of here in no time. Okay, so here are this week's tests back.
Oh my gosh!
Okay.
I made an A! Oh, here you go, Andrew.
Oh, my arm's tingly. I think I'm having a heart attack. Oh.